The battery ground fault tracer locates ground faults in ungrounded DC battery systems. Various standards require action when the impedance between any battery polarity and earth ground falls below a specified limit. In the case of nuclear fuel plants, the Nuclear Regulatory Commission requires audits and appropriate action when this impedance is deemed unsafe. Other facilities come under the guidelines of the National Electric Code, NFPA, IEEE standards, and OSHA requirements for safe operation of DC battery systems in an ungrounded environment. How the BGFT works. The BGFT applies a 20 Hz signal between the battery bus and station ground. This is accomplished by connecting the transmitter via the source leads to an accessible battery bus and to a ground bus located in a distribution cabinet. A two-step process then begins to identify both the magnitude and location of the fault. First, suspect feeder cables are identified by measuring the flow of fault current to ground on all the output circuits from the cabinet. Then a bridge balance measurement is performed to determine the value of capacitance and resistance of the suspected ground fault. Once a ground fault condition is revealed, either through monitoring equipment or inspection, the battery ground fault tracer can be used to identify, track, and locate the fault or faults in the DC distribution system. No ground identified on the negative bus. The positive bus clearly shows a ground fault. Initial transmitter settings. Set output voltage switch to disconnect. Set voltage control fully counterclockwise to minimum. Set all capacitance selector switches fully counterclockwise to their minimum position. Set the resistance selector switches fully clockwise, with the leftmost switch set to open. Connect the current source leads to the voltage output jack J3. Insert by lining up the keyway with the receptacle slot and push in and turn to the right. Attach the red source lead to the positive post of battery cell number 1 or any one of the battery bus connections suspected of having a ground fault. Attach the black source lead to the system ground connection. Turn the power switch to the on position. The capacitance and resistance controls should be set in their initial positions as outlined earlier. The ready indicator will illuminate, indicating the readiness of the transmitter power oscillator. The output voltage connect switch can now be placed into the connect position. The amount of test voltage required will greatly depend upon the magnitude of fault impedance to be located and the system requirements for injecting signals onto the distribution bus. Connect the two parts of the receiver, the clamp-on current probe that surrounds the cable to be examined, and the display and metering unit. Remove sufficient cabinet work to expose the DC supply bus feeder connections. Begin tracing the ground fault by clamping the current probe around the cable coming in and out of the breakers. The faulted cable will be identified with a measurement of current on the receiver meter. The ground fault has been identified at circuit breaker number 6, the data center. Defining the fault impedance is a better, more accurate method to locate ground faults. You can locate ground faults by tracing the circuits with the higher receiver values without using the feedback loop to determine which faults are real and which are phantom. Phantom faults are caused by high capacitance sections. It is recommended, however, to use the feedback loop on the first panel to possibly eliminate high capacitance sections. Then, while leaving the transmitter at its location, use the receiver to trace all other high readings until all faults are located. A feedback cable coupled to a decade bridge that defines the true impedance and allows a true resistance value of the fault to be recognized is used to help eliminate false impedance to ground. With the feedback control switches set to the blue numbers, start with the capacitance section of the bridge. Observe the receiver display and dial in a capacitance from the bridge section. If the feedback cable is properly aligned, the display reading should start to decrease or remain the same. If the display value starts to increase, then the feedback cable is entering the current probe from the wrong direction. Either reverse direction at the transmitter panel or change the orientation of the cable at the current probe. If the display value remains the same, then the fault impedance is resistive. in content and no further capacitance nulling is required. Note that the molded banana plug on the feedback loop lead is tabbed. The tab plug inserts into the negative input of J2. Place the feedback loop lead through the current probe and then place the current probe around a non-faulted feeder. The feedback control on the transmitter will be used to balance out the unwanted phantom current. While watching the current reading on the receiver, begin to adjust the capacitance switches until the receiver meter shows 0. Our tracing efforts have taken us to the RTU cabinet. Our ground fault has been located in the RTU cabinet. No ground fault is detected coming out of the RTU cabinet. To simulate a ground fault, we used a light bulb connected across the positive bus and ground. As we can see, once the light bulb is removed, the fault is cleared.